Hi, I'm Ratnesh, and I'm presenting on this work, post tracking by exploiting global features. This is done at Virginia Tech with Dhruv. This is the outline of the talk. So I'll explain the basic machinery of the post tracker and explain the approach and finally conclude with the results. So this is basically a detection by tracking approach. So I have multiple post detections in every frame, and I needed to stitch and get a reliable post track satisfying color homogeneity and motion homogeneity, and the computation should be efficient. This is the basic machinery of a post tracker, of mini post tracker. It's a chain CRF. Each column indicates a frame and plausible post detections in the frame, and the edges indicate affinity between two detections on the lying on successive frames. And the goal is to find a post track such as the edges indicated by red. Um, the good thing about this model is that it's computationally efficient and we can find a global optimum in a polynomial time using dynamic programming. Uh, however, however, there are some top shortcomings in this approach, is that we have only pairwise successive frame edges and no global edges to deal with ambiguities such as drifts in tracking. And when we naively try to incorporate such edges, it may increase additional complexity and inference becomes intractable. So this is the outline of our proposed approach. So to deal with computational explosion, we first try to extract multiple post tracks from a base model, and then in this tinier solution space, we incorporate lots of global and local features to obtain a better post track. Zooming into the approach, for computing the different post tracks, we use the basic machinery of Butler et al. In ECCV 2012. So basically, we compute m different post tracks in an iterative manner. At every step, we impose constraints so that the the next solution is significantly different than the solutions which we found. Now the solutions which we found are needed to be re-ranked automatically. So this is an illustration of different post tracks. So this is basically one post track of three different joints, and with our diverse solutions for each post track, we have m post tracks for each of the joints. So m green track, m blue track, and m red track. And the goal is to re-rank this using different scoring functions. So one of the scoring functions which we use. So now I'll go through the scoring functions. So one of the scoring functions is the color similarity measure. So instead of measuring the color similarity between only pairwise successive frame edges, we measure it between all of the possible edges in a track for all the tracks, and the affinity we use is color histograms between bounding boxes. Similarly, for motion, we can compute the motion affinity between all possible pairwise edges using point tracks. The picture is an illustration of at four different frames, different detections, and our goal is to maximize the amount of sharing of point tracks, or to choose a track which has the maximum amount of sharing of point tracks across time. Point tracks means pixel tracks. Another motion-based measure commonly used is acceleration penalization or curvature penalization. So basically, trajectory should be as smooth as possible in time, which can be obtained by penalizing Laplacian of the centroids of bounding boxes, which are indicated as Pi, located at three different timestamps. So this is a third order function. Um, Another unary term that can be added, which is important when there is a lot of motion, is the motion boundary. The first images show successive frames, and the third image is the color-coded optical flow, and the fourth is the spatial gradient of optical flow. And you can see that the near high moving areas such as this, we have lots of gradients and can help in localizing this. So this is the summary of the scoring function which we use, and each track is ranked independently using the scoring function. This is some of the quantitative results. So we use the base map model by Anup Cherian in CVPR, and you can see in the table that the first row and the last row a significant improvement. This is an example of qualitative results. The first row is the map solution from the base model, second is our solution, third is the Oracle solution. You can see in the second column that a track gets locked to something on the table, and we have a better solution than that. So there are some things which we can improve on. We'll talk more about this at the poster and see at poster 2.